Okay, I wanted to go over Lab 2, which for some of you will be challenging, for others of you it will be easier. Yeah, everybody handles these things differently also. So when you do Lab 2, there's two PDFs that I've linked on our homework page, and if you open them up, they will open up like such, okay? And so I'm actually going to pretty much do almost the entire lab here in class, but I'll just kind of talk through them quickly, and I will have you guys do it yourself at home as an exercise. So yes.
Are you recording this?
I am recording this, okay? So it will be as a reference. You are always welcome to come closer. You can even sit at this table. Might feel a little awkward, a little too close, but so just a word of warning. I don't recommend highlighting and copying and pasting, just because sometimes there's these invisible characters or invisible spaces or things like. And it might not even be a space, it might be a non-breaking space which looks just like a space, but the computer handles it differently and can cause errors. So, some of these commands are a little bit longer just because they have a web address, but I strongly encouraging just typing the commands out yourself rather than copying and pasting, because depending on whatever, it might insert breaks and spaces in the wrong spot, or the worst, the invisible non-breaking space that you can't tell is not really a space until it errors out on you. So, what's that? It can be quite annoying when you're searching for an error and everything looks correct, but the computer, so you have to turn on special characters and you're like, this thing. So okay, so anyway, I have done that already, and again, so when you run R, it probably looks. Oh, something happened. Okay, let's see if I can fix that. Oh, it's probably going to freak out on me. Output to clone displays. Good? Yep. Okay. So what I recommend is creating a new file, new R script, okay? And that will create a blank document, and that's actually what I have started over here, and that's where you would type in your commands. So then if you encounter an error, you can just look through this thing and look for the problem there, rather than having to retype all of your commands. Okay. So anyway, the first one is download.file, and then the second one is you load it. Now sometimes, depending on your computer, your computer might error out on this very first line, which is download file, because there's it has to open up a connection within R, and for some reason, some computers, it doesn't like to do that. So if that's the case, just copy this link into a web browser and download the file into somewhere onto your computer, and then you can browse to it in this files section. And then you can click, and if you find the data file, you can just click it, and it will say, do you want to load the thing? And it will load that way. Okay, so if you encounter problems with the download.file, you can download it manually through your web browser. Should be no problem. And then you'll just navigate to it under this files thing and load it. Or you could do file, open file, okay? And you can open the file that way as well. And if it's as long as you save it with the .rdata extension, it'll recognize that this is rdata, and it'll load it properly rather than trying to open it as a text document. Okay, so anyway, when you do that in your global environment, you should get the data set as well as two functions. So it has two functions already pre-programmed in there, okay? And what this is it's real estate data from the city of Ames, Iowa. And we're looking at things like, here, I'll just show you what it looks like. Just housing information, you know. There's property ID, but then also just how much area is on the land, how many square feet the area of the house is, and just all sorts of little bits of the living area, which is square footage of the house, how many bathrooms, how many bedrooms, and etc., and how much it's sold for. Okay. So there's lots of things, some of it categorical, some of it numeric. We're just going to look at just a few of the numeric variables here. Okay. And so just to make our lives easier, we're going to create this thing here. Okay. So we're going to create a vector called area, and into it we're going to take from the Ames data set greater dot the living area, which is just the square footage of the house, and then for price we're also going to take from the Ames data set the sale price. Okay, and then so when you type your commands into the script, which is not the console, it doesn't run those commands. So if you want to run them, you just you go back to your line, you put your cursor on one of the lines, and you hit Control Enter or Command Enter if you're on a Mac, and it will execute the line. Okay, and then so now we can see within the data set I've got area and price, and I've got 2,930 observations. Okay.
So wait, sorry, how do you load it again?
You just hit, you go to the line that you have written that you want to execute, and you hold down the Control button and you hit Enter. Or you could also hit this button with the mouse that says Run. That will run it as well. It's the same thing.
Last time it looked like you were highlighting groups of them. Is that?
Oh yes, you can highlight multiple lines, and you can hit Control Enter as well, and it will run both of them. Okay. All right, and then so I could ask, you know, give me the summary of area. Okay, and here it does that. Create a histogram of area as well, and it plots it right here. Okay, and so we could see if I make this histogram larger, we can see that the data is right skewed. Most houses between 1,000 and 2,000 square feet, some smaller, and then we have a few houses much bigger, you know, 5,000 square feet, something like that, within our data set. Okay, so it's gonna, you know, exercise 1, describe this population distribution. It's got this median, it's got this mean, right skewed, etc., etc., etc. Okay, what we're essentially going to do is we're going to create a sampling distribution based on this thing. So we see our population has a skewed distribution, but we can take random samples. And I think I skipped over one of the commands. Yes, right here. Okay, so here we're going to create a sample. We're going to just select 50 of the houses, or 50 of the values in area. Okay, so area is just, so we're going to create sample 1, and we're going to just take values from area, and I'm going to take 50 of those. Okay, and so if I look at samp 1, we could see that there's 50 values, and they're just randomly sampled from the vector area, which has 2,930. Okay, now we could ask, what is the mean of samp 1? And the mean of the random sample that I selected, 1,430.6. So we are going to generate a sampling distribution, okay? And so, you know, read through all of this text. It talks about it and stuff. But what we are doing in this portion of the lab is that we're going to generate a sampling distribution, okay? And so we are going to create a loop, and we're going to store the values of our loop in this vector called sample means 50 to represent that we are taking samples of size 50. Okay, and we're just going to stick in zeros, 5,000 of them for now. Okay, and then we're going to say for I in 1 through 5,000, curly brace, we're going to generate a sample, which is we just say do sample size 50, and then we're going to store the mean of that sample. Sample means 50 into location I, the mean of that sample. Oops. So I did this last week in to demonstrate creating sampling distributions, but you guys will do this yourself, okay, in the lab. And it, again, don't try to copy and paste this text here. I know it feels like a lot to type. Just type it exactly as you see it, all right, and run it that way. I mean, it might work if you copy and paste, but chances are it's going to put a space in the wrong spot because it's reading from a PDF. It's not nice to copy from. Okay, so we ran it. It doesn't look like it did anything. We're going to ask to create a sample, a histogram of sample means 50. And let's see what it does. Okay, and so there we have it. Here is our histogram, and this looks much more normal shaped. Okay, and as I always like to do, we can increase the number of breaks so that it looks a little bit, quote, nicer. And here's our same histogram, but with additional breaks. And this looks nice and normal shaped. So these are the means of samples. We took 5,000 samples, each sample having 50 values. So yeah, pay attention. I guess know that you've taken 5,000 samples, each sample having 50 values, because our the question in these labs ask you what would happen if you changed, you know, this number to something else and this number to something else. So they explain how the loop works and all of that, which I'm going to skip over. It's good for you to read, especially if you are relatively new to programming. If you know how loops and all of that stuff works, then that will just be easy, okay? We can do the same thing again, except this time taking samples of size 10 and samples of size 100. And we can do sample means 10, sample means 100. So I don't hesitate copying and pasting text from within my own script that I've written. But for trying to copy and paste text from a PDF, I have learned generally causes more headaches than it's worth. Especially if it's manageable. And a lot of times you learn from copying line by line.
What are you pushing to get it to like indent like that? So for
That actually, it automatically does that when I create a for loop in R, and I'm used to it automatically prompting me to oops. With you know, kind of this autocomplete thing, which I guess doesn't work on everybody else's computer. So I don't know. I don't know what the why it autocompletes for some and not for others. I did not. Yeah. Yeah, I don't think they've jinxed their system that way, or nerfed their system. Yeah. No, I don't have $1,000 to pay for I don't know, support. Okay, so it already ran, and we haven't seen anything, but I can ask, you know, for histograms of sample means 10 and how that compares. Okay, so we can see with sample means 10, and even if I do breaks equals 25, we can see that there's still a little bit of skew in the inner histogram, okay? So it's almost normal, but there's still just a tiny bit of skew. But as we increase the sample size, that artifact goes away. And so here, this looks much more symmetric. Okay. Oh, and it creates it asks you to create this thing called X limits. So these commands here basically allow you to plot multiple histograms into one thing. Okay, and you can follow these instructions: par mf row, which says make 3.1 says put 3 plots and 3 rows and 1 column of plots. Okay, and we're creating a vector called X limits, and for that we're just asking the range. Sample means 10 because we know that's going to have the largest range. Oops. And I'm going to just basically do a histogram of this. X limits of the graph is equal to X limits. All right. And then I'm gonna anytime you do par something, it's good to undo what you did at the end. And I don't know if that shows up in our oh, it does. It does say do it at the very end. It's just a little footnote, but it's good practice because it could mess things up. Okay, and so here we go. This is what it looks like. 3 histograms all on the same scale, from 1,000 to 2,400. This is the samples of size 10, samples of size 50, samples of size 100, and we could see the spread gets smaller and smaller and smaller. Okay, anyway, you're going to do this. It's going to say basically do the same thing except use the price vector, which is very skewed. Change your samples from 50 to whatever, etc., etc., etc. Okay? So that's one part of the lab. And then the other part of the lab is we're going to create a bunch of confidence intervals, okay? You don't need to reload the data set. If you've already loaded the data set in for the first part, you don't need to do it again for the second part. And essentially, we're going to just assign, we're going to create something called the population, which is the same thing as the area. We're going to take samples from the population of size 60. and we're going to have it create confidence intervals, okay? Now, just in this lab, they chose to use 1.96, and that is technically not the correct value to use because we're supposed to use the t, a value from the t table, which is not going to be 1.96. So in this lab, this is technically not correct. They are using 1.96, which is not the true value. We should be using something from a t table. But for the purposes of the lab, we're going to just kind of ignore that, and we're going to create confidence intervals with that value anyway, okay? But if you're wondering, why are they doing that? Is that right? The answer is no, it's not correct. It should be, look up the t value based on the size of your sample. And we're creating a lower value, sample underscore mean minus 1.96 times the standard error, which we calculated. And then we're creating a value upper. Did I mess something up? Yeah, I forgot that line. So sometimes you're writing our code and you get error messages, okay? And when you read the error message, sometimes the messages seem cryptic, okay? But try to understand what the error message is saying. And oftentimes it's not as terrible as it might seem. So here it says object sample underscore mean not found. So that means, hey, wait a second, you never told me what sample mean is. And I looked back in my code, and indeed I did not. So I have to tell it, define what sample mean is. So this is where it errored out. And then so now I can run this thing. And it's giving me 2 NAs. So let's see why is that happening. Sample the population. Argument is non-numeric. Oh, see? So if I look at my code, it says warning, mean and mean.default sample argument is not numeric or logical, returning NA. Okay? And so here I said give me mean of the sample, but that's actually not what I should have typed. I should have typed in mean of samp. Okay? So because I was sloppy in my typing and I typed sample and not samp, it errored out. And that's so everything else that depended on that also errors out, okay, or it gives me not what I'm expecting. So a lot of times, if you've done coding before, you're used to this debugging process of searching for a small little mistake that can cause problems. So they always say, work in small little chunks and make sure that little thing works first before trying to do like 600 lines of code and then running it at the end and then searching for the one line that messed up. Okay, so this behaves the way I expect it to. So it's giving me a lower and an upper bound of my confidence interval. And then they've already created a function that plots the lower and upper bound, okay? But what I can do is I can create an entire vector of lower bounds, an entire vector of upper bounds by creating this loop, okay? So we're going to create a loop. We're going to take the mean of the population, and so I'm going to create samp underscore mean, and we're going to create a vector of 50. I've been off this whole time. I'm so sorry. We're going to create a vector. Oh gosh, wait. Now it's too much power. All right. Sorry. I guess you guys heard me okay, because nobody said anything, but, and maybe now this is too loud, I don't know. If I'm not coming in loud, just say, I don't think your mic is on or something, you know? Sometimes I forget to turn things on. Okay, so here we're going to take samples of size. We're assigning n to be 60. We're taking samples, and I'm creating vectors of zeros as placeholders, which will be filled in when I run the loop. So same as before, I'm just running the loop for I in 1 through 50. And we're going to do make a sample. We're going to draw from the population a sample of size n. Samp underscore mean, and into samp underscore mean I'm going to store this information, the mean of the sample, as well as the standard deviation. So we're going to run this loop, and this is going to generate 50 values in samp underscore mean and 50 values in samp underscore standard deviation, which we can take a look at if I wanted to. I could see all the 50 samp underscore mean. There will be 50 values here, and same with the standard deviation. Now I can work with this and just say, okay, for the lower bound, what I want you to do is I want you to take all 50 of those values. Samp underscore mean represents all 50 values, and I want you to do subtract off 1.96 times samp underscore standard deviation divided by the square root of n, which is 60. And it's going to run that for all of them. And it knows to match the first one with the first item, and the second mean with the second standard deviation, and the third mean with the third standard deviation. It kind of does this kind of like dot multiplication, and it matches them all, and then we can have them run both of these things, and then so lower and upper both have 50 values in them. Okay, and now I can plot them all using this confidence interval function that it has already been pre-programmed in here, which is, it's a nice little function. Plot underscore ci, lower, upper, and against the mean of the population. Okay, and so this is a nice little function that it has been created for us. And so this dotted line represents the mean of the entire population, which is almost exactly 1,500. It's ever so slightly off, 1,499. And here represents a random sample that has this mean, and when you create the confidence interval, it goes out to the upper and the lower. Okay, and so actually all of my confidence intervals happened to capture the mean, but let me this one barely got it, but it did. Okay, and that looks like the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13th number. So if I looked over on the lower bound, the 13th number, the 1356, why is that no? Or is it the upper? Let's see. I'm not sure. Maybe I counted wrong. 13, 12, 13, 1499. One of these barely, oh, it's 13th from the bottom. Okay, 1498.92. Okay, the true mu is 1499, and this barely got it in by saying the lower bound was 1498.92. So it barely got it, but it did. But if I if I ran this code again, and let's just do that, and it plots it. So here we get one. This one did not capture the true mean of the population. Okay, so as you play with this, with a 95% confidence interval, we're expecting about 5% to miss, and so I've run about 100 of these and only one have missed so far, but these are just random samples, and so if I did this again, here I get 3 that missed, and so on and so forth. So as you do different samples, your samples might end up leading you out here. And again, it's not correct for us to say there's a 95% probability that mu is in there, because mu is fixed at 1499.69. It doesn't move around. There's no uncertainty there. But we can talk about, looking at this confidence interval only. Are we confident that it captured mu? We can be 95% confident that it did. It would be correct to say there is a 95% probability that the next sample I take will produce a confidence interval that captures the mu, okay? Because there is uncertainty as far as the next sample you take. But once you've taken the sample and determined the sample mean and created the confidence interval, there's no more uncertainty there. There's never been any uncertainty about the mean of the population, so it doesn't make sense to talk about probability in that example. Okay, so anyway, you're going to work through this. Depending on different factors, luck being one of them also, it might take longer than you'd like. Don't spend more than, I would say, 4 or 5 hours, okay? Especially if you're running into the same problems. And if you keep getting a certain error message or something and you can't figure it out, don't hesitate to email me and include the commands you're typing and the error message you're saying, and I might be able to at least decrypt what the error message is saying and what's going on.
Can I also just say that as a programmer, one of our secrets is that a lot of what I get paid for is Googling error messages. So
Yes.
just Google error messages. Just
Goog-
copy the whole thing, paste it into Google, find out something.
Yeah, there's Stack Social. There's always pretty much all of those things are just like, well, what do I do with this error message? And exactly, a lot of my learning has also happened through what does this error message mean, learning from it, and then doing better like that. Okay, so again, some of you are comfortable with this programming stuff, other of you are not. I think it's a very good skill to have in your life. And I know some of you hate it, right? But it forces you to kind of think in a logical way. And here you don't even have to think about programming things. This is just following, paying attention to the small details and making sure you're typing in things correctly. But even that is useful as well. All right, so in our last bit, let's just review some topics for the midterm exam. Make sure you can handle everything. Okay. So I'll have a few things on I guess descriptive statistics. So make sure you can calculate the mean, median, quartiles. Okay. Also the IQR, range, and standard deviation. you should also have an idea of kind of like definitions of each of these, not just how to find it, but like what do these things represent, okay? So for example, the mean, what does that represent? Not how to find it. How to find it, you add them all up and you divide by how many you have. But what does it represent? We think of it as the balance point of our data. You know, the median is the what? Halfway point. Half are larger, half are smaller. Quartiles, I guess, would be quarter points. You know, a quarter is smaller, or 3/4 are smaller. Okay. Standard deviation, what would that represent? Maybe typical distance from the mean. Okay. And the power, the true power of descriptive statistics is their ability to compare one set of data to another with just a single number, right? Okay, and so know how to find all of them, but also what they represent, okay? Okay, so you should also be able to understand and interpret different displays. Okay, so I'm drawing a blank here. Box plots, histograms, dot plots, bar charts, okay, and be able to look at one and draw the answer questions based off of box plots and histograms. Right, it's a multiple choice exam, so I can't ask you to draw. I can't ask you to draw one. So. If I showed you a box plot like this, and I said the underlying data is ... symmetric, left skew, right skew, or unable to answer with the chart. You would say right skew, okay? Right skew means wherever your middle is, which will be somewhere around here. I mean, it'll probably be drawn out a little bit, but you've got values much larger than that, but none going in the opposite direction, much lower, right? Or, you know, if we look at, you know, where the 75th percentile is, it's right here, and so you've got values way higher than the 75th percentile and 20, you know, so you can assume that the underlying data looks something like this or something like that, right? Okay. All right. So anyway, be able to. So that's stuff on descriptive statistics. Okay. And we're gonna have probability questions. So if I show you, a chart, and I've got, A and B and C and D, you should be able to answer what's the probability of A, what's the probability of A given D, probability of D given A, okay? Also, so I should be able to ask questions in this form. Also, I can ask in words, right? What is the probability of, whatever A says if we know D is true, or something like that, okay? Of course, I'm not going to say A and D, but so, be comfortable with that. Be able to do things with the tree. So, for example, probability of, some disease is, 0.1, and probability of positive test given disease is 0.98. Probability of positive test, no disease, is 0.1 or something. That's a terrible test. Let's say 0.8. Still a terrible test. Okay, well, anyway. You don't want to have a test with only a sensitivity of 98%. It's not a very good test. 2% of people are slipping through. But anyway, so this is a terrible test in some disease that's pretty common, apparently, at 10%. It's like, well, anyway, okay, so, you should be able to answer questions like, what's the probability of actually having the disease if you test positive, right? And this might be written in words rather than symbolically here. So you're going to have to make the tree. What else do I have? Maybe just also just regular old basic probability questions like that might involve you. I'm not going to draw the Venn diagram, but I could say 0.35 of houses have cats, 0.40 of houses have dogs, and we'll say 0.12 have both cats and dogs. And I might say what proportion have cats but no dogs? Can we do this? So let's label this. What goes in the middle here? 0.12, right? Both cats and dogs. So if A is, we'll call it cats A and dogs B. So 0.12 goes in the middle. All right, so how much is A total? So that means how much has to go over here? 0.23, so that the entire circle is 0.35, right? So the answer to our question here would be 0.23. Yeah. And then over here we would have 0.28. I could also ask what proportion have, or what cats or dogs? Cats or dogs? And you would tell me. I'm sorry? I'm getting 0.53.
Oh, yeah. Well.
Yeah. Yeah. So you know, add these two and subtract off the overlap, or if you drew the picture, you could just add the three numbers up separately. Yeah. However you do it. Okay. So questions like that. Of course, not exactly the same as that. Binomial problems. And normal distribution problems. And normal approximations to the binomial. And I'm not going to say this is a binomial and this is normal. I might say use a normal approximation to answer this question, because technically those are binomial questions, but so I'll probably say use the normal approximation. So this one I will at least say use normal approximation.
And then assume that they're without continuity.
Yeah, they'll almost always be with continuity correction, okay? Because there's ambiguity with, if you don't say with the continuity, if you do it without the continuity correction, there's always some ambiguity. Right, because if I say at most 10, do you draw your line at 9 or do you draw your line at 10? Or 11? Well, I guess at most 10 would be 10 or 11, and you know, it's hard to say. So I'll say with the continuity correction, and then there's no ambiguity, you do it at 10 and a half if I say at most 10. Okay? Binomial normal, I'm not going to say which is which. Oh, I also forgot random variables, right? Random variable problems. Where you know, you're given a chart that says x can take on values 1, 2, or 3 with probability, you know, 0.5, 0.2, and 0.3 or something like that. You know, find the mean, find the standard deviation. And the random variable problem might be written in words. I might not. Well, we'll see. Okay.
But I'll have the chart.
I don't.
Or if the chart will be written.
It'll be at least written in words, right? It might say like the number of doctor visits in, you know, follows the following probability distribution, you know. 50% of patients visited the doctor one time or something, et cetera, et cetera, et cetera. I wonder what the average number of doctor visits for the entire population is.
Depends on the city, I'm sure.
Depends on the city.
You're talking
Per year, yeah, per year.
before or after a work.
I don't know. Yeah, that's a good question, right? Somebody should do. I'm sure somebody has done studies.
I think the AMA just
And no
recommended.
number of hospital visits is down.
Yeah.
Well, that's good.
The AMA just recommended yearly checkups be eliminated.
Yeah, I never did a yearly checkup. I think there was a time when I was shortly graduated from college that I didn't go to the doctor ever. But I went to the dentist at least. So maybe that counts. 'Cause they kind of check your health when they look in your mouth. At least they know. Well, anyway, right? If something is severely wrong, that will be identified during a dental visit. Well, maybe. Yeah. Something wrong with your teeth, they will. What else do I need to say? Okay, confidence intervals, of course, and sampling distributions. But I'm just trying to think. So, everything, pretty much everything that we've covered is fair game. But I think, yeah, so I don't feel like writing this, but okay, I'll write it. So sampling distributions, confidence intervals, both for 1 and 2 samples. For confidence intervals, be sure you know the proper interpretation or proper conclusion that can be made from a confidence interval. Right. It's always a conclusion about the mean of the population. Never about the sample, never about future observations or anything like that. It's always about the population. And we say we're confident, we're not making statements of probability or anything like that. Okay, I think it's a good exam. We'll see you guys next week. Good luck as you guys study.